Grimes teacher here. Let's take a look at 2007 higher level paper question 2 for physics, and this is looking at a question on specific heat capacity.
Right, pause the video and give yourself 20 minutes to attempt this problem. It's an experiment question. 20 minutes is the max amount of time that you can allow for it. And now the solution in 3, 2, 1, go.
So, reading the question, the specific heat capacity of water was found by adding hot copper to water in a copper calorimeter. They tell you a bunch of data is recorded. Describe how the copper was heated, we'll get into that, and how its temperature was measured. Using the data, do some calculations, and then give 2 precautions that were taken to minimize heat loss to the surroundings, and explain why adding a larger mass of copper would improve the accuracy. Just a thing to note in the exam, or the previous papers, is that quite often they give details at the end of a question as well in brackets, so just if you're looking for something there. Now, let's go through this piece by piece. The first part, describe how the copper was heated, how its temperature was measured. So a quick sketch of how this one was done. What I had some copper pieces and I added them into a calorimeter full of water, right? Now the copper pieces were heated, and in the question they heated to 99.5 degrees. Now, I'm not answering the question, I'm just talking you through the theory here. Describe how the copper was heated. Well, what I usually would be doing in this case is I need to heat the copper up to some sort of known temperature. So what I do is I get a thing of water and I put it on a hot plate. So I have a hot plate, I have water, and I get it to be boiling. Okay, boiling water should be at 100 degrees Celsius, all right? I place my copper pieces in there, I'll do them in blue. And now they should, after a short period of time, be 100 degrees copper pieces. So that's how the person heated it. Now, the question though asked, describe how the copper was heated and how its temperature was measured. Well, reference of any source of energy here, so hot plate providing energy, providing heat or providing energy. And then how do you measure it? Well, give them some sort of way of measuring it. You maybe had a temperature probe hooked up to degrees Celsius, so a temp probe, temperature probe, or you could say a thermometer. Okay, I'll just call that part A because they didn't list them back in the early years, so I'll call that part A. Part B will be using the data to calculate the energy lost by the hot copper. So he's actually broken this problem up into 2. He's broken it into energy lost first, so we'll do that. So the energy lost by the hot copper. So first off, it's just changing temperature, it's not changing state, so it's MC delta theta. So taking a look, I have the mass of the copper I need to find. So he's given me in the question the mass of the copper, the calorimeter, and the water. So to get the mass of the copper, I would need to subtract the mass of the calorimeter and the water. So to get the mass of the copper, I would need to say it's the mass of all 3, mass of copper plus the mass of the water plus the mass of the calorimeter, minus the mass of the water plus the mass of the calorimeter. Okay, so with that in mind, I'm going to say it's 131.4 minus 101.2, and I get it to be 30.2 grams. So the mass of the copper is 30.2. I'll use copper is 30.2 grams, and divide that by 1,000 to make it kilograms. So instead of writing it as grams, I should always write it as kilograms. 0.0302 kg. Specific heat capacity of copper is given at the end of the question. And the temperature change of the copper. The temperature, it started at 99.5, and the final temperature of the water. The water now includes the copper, so that's the final temperature of the copper as well. So the temperature change of the copper pieces, I'll call it the cop, is 99.5 minus 21, ends up being 78.5 Kelvin. And then just plug it into the equation. E equals the mass by 390, which is the specific heat capacity of copper, by 78.5. So on my calculator, multiplied by 390, multiplied by 0.0302, I get this to be 924 0.573. It's a leaving cert, don't forget your units. It's energy, so it's joules. You lose 1 mark in the leaving cert generally whenever you drop a unit. Not all the time, usually only punishes you once in a question, but let's just always cover ourselves. So we've done the first part, the energy lost by the hot copper, and now the second part, find the specific heat capacity of water. So part 2 of this. To find the specific heat capacity of water, what we have to do is we have to start with the equation of heat lost equals heat gained. And the heat lost in this scenario, in this quick sketch, was by the copper pieces. And the heat gained is by 2 things, by the water and the calorimeter. So the water and the container, the calorimeter. Okay, I say cal for short. So over here, heat lost by the copper should equal the heat gained by the water and the calorimeter. Now, what I'm going to do before I get tucked into it here is I'm going to list out the mass of the water, the mass of the calorimeter, the specific heat capacity of water, and the specific heat capacity of the calorimeter. And also the temperature change of the water and the temperature change of the calorimeter. I always recommend listing these off when you're doing these problems because you're going to need them. And you can also get attempt marks quite often. So let's have a look for finding the mass of the calorimeter. Well, that's easy enough. It's given so it's 55.7 divided by 1,000 makes it 0.0557. So kg. The mass of the water is going to be 101.2. So this figure here, take away the mass of the calorimeter, 55.7. I'm doing that in grams and then I'm converting, so I'm dividing by 1,000 to convert to kilograms, and I get it to be 0.0455 kg. Specific heat capacity of water is what we're being asked to find, so I don't know that. The specific heat capacity of the copper calorimeter is 390 joules per kg. The temperature change of the water and the temperature change of the calorimeter will be the same. The final temperature was 21, the initial temperature was 16.5. So I'm going to do 21 minus 16.5, and I get that to be 4.5. And that's the same for both of them because they're both in thermal equilibrium. Now that I have everything, I think I'm good to go. So what I'm going to do is I'm going to drag this stuff and put it down here as well, just so I can work with these numbers. And I'm going to say the heat lost by the copper. Well, we did that there already, so we actually have that number. It was 924.573, so I'll copy that into my little arsenal there, and I'll put it over here. There. Equals the heat gained by the water. So the heat gained by the water is mc delta theta. And the heat gained by the calorimeter. There's no latent heat or changing state here, so don't start putting in ml like a loony. That's all waters. This is all C for calorimeter, I'll say. And now I'm just getting ready to do some plugging in and solving. 924.573. Mass the water by specific heat capacity of water, so I'll zoom out a bit. I don't know that, that's what I'm trying to find. Temperature change of the water was 4.5. Plus the calorimeter mass, which was 0.0557 by 390 by 4.5. So on the left hand side, nothing changes, 924.573. On the right hand side, I can multiply this number and this number. So 0.0455 multiplied by 4.5. I get this to be 0.20475 CW plus, multiply these three numbers together, 0.557 multiplied by 390 multiplied by 4.5. I get this to be 97.7535. Bring this over to the other side and change the sign, so subtract it from the other side. So I'm going to say 924.573 minus that value over there, and I get it to be 826.8195 equals 0.20475 specific heat capacity of water. Now, divide this side by this number to get rid of that. And that means also divide this side by 0.20475. So on my calculator, I say my answer there, divided by 0.20475. And I get the specific heat capacity of water, CW, equals 4038.2 degrees Celsius. Okay. And that there is my answer. Oh, sorry, no, careful. Degrees Celsius, what am I talking about? I'm talking about specific heat capacity. That's not in degrees Celsius. That's in joules per kg per Kelvin. Okay, so be careful of going too fast, too furious when you're doing a question. Always check your units at the end. The accepted value is approximately 4,180, right? And we got 4,038. This is actually perfectly fine. This is experimental error for sure. There could have been many reasons, which actually is probably what the C part here is going to talk about. So, give 2 precautions that were taken to minimize heat loss to the surrounding. So another question he might have asked here was, why is the answer not as accurate as it should be? And you could say, well, heat was lost to the surroundings. That'd be valid. But here he wants 2 precautions. Sorry, when I say he, I mean the examiner. It could be a she. But they want 2 precautions to minimize heat loss to the surroundings. So one precaution would be to insulate the sides, insulate the container. Okay. You can say a lagging jacket or something like that. Another thing would be to use a lid, right, on top of the container. You could also say avoid splashing here because we've got adding copper pieces, so there's a chance it could splash. And then other things like you could start the temperature slightly, use cold water, like slightly below room temperature. That's to even out with the temperature lost, the surroundings should equal to the temperature gained from the surroundings. Any 2 of those would probably be fine. Let's have a look at the D part then, or the last part. Explain why adding a larger mass of copper, so why would adding mass of copper improve the accuracy of the experiment? So make sure to touch on these points. Now, you can say this as simple as literally smaller percentage error, and you would have got the marks. Okay. But let's just talk about that for a minute, of what that means. Let's say, for example, you have you're able to take the temperature and you can be plus or minus 0.1 degrees within accuracy, right? So if you add larger mass, you're going to get greater temperature changes. So more mass means greater change in temperature, delta theta, right? Let's just see the difference. Let's say we've got 0.1 degrees Celsius for the things that we can measure on our, like we can measure 1.1 or 1.2 or 1.3, right? That would mean that we could potentially, it could be this amount off plus or minus, right? If we're measuring up in increments of 0.1, sorry, I meant to say there, right? So if that's the case, well, let's just look at how that affects. What happens if you do a temperature change and it's just 1 degree, right? That would actually be 1 degree, but it could be plus or minus this value, right? In your answer. So let's just see, what's the percentage error in that? Well, you take what it could be out by, divide by 1 and multiply by 100 to make it a percent, and this would tell you there's a 5% error, right? Conversely, if you do it for this guy where you've got 10 degrees and you still could be out by this much, then put this number, divide by 10 and then multiply by 100, and here you'll see, he grabs a calculator to be sure, it's a 0.5% in the error. Okay, so if you use much larger temperature differences, greater temperature differences, how do you get greater temperature differences? You need more mass. Now, so far this maths hasn't been asked in Leaving Cert Physics, so don't even worry about that. It's just coming to this idea of smaller percentage error leads to you want to have smaller percentage error in your answers. Okay, so that can be done by adding more mass. Okay, again, you don't need that explainer. Right, let's look through the mark scheme and see how we got on. So here's the mark scheme for 2007. Describe how the copper was heated as temperature was measured. Any source of energy for 6 marks. Well, that's nice. And a thermometer, temperature sensor, a probe, reference to 100 degrees if you're boiling it in hot water. So let's see, did I mention yes and yes? So 6 marks for that, and mention of this and a temperature probe for 3, and boiling hot water. So we kind of had both covered. Part 2, or part B1 as I called it, 924.57 or 924.6 joules, 924.6. He's not going to punish you, or they're not going to punish you, excuse me, for being more accurate in that regard, so you're totally fine with that answer. Next part, the heat capacity. Heat lost by hot copper equals heat gained by the calorimeter and water. Stated or implied, 3 marks. So actually just for this we get 3 marks. That's nice. And then shown it all plugged in, obviously with the number you got previously, okay? And sure enough, we've got that there. We just have the opposite way around. So we have another 3 marks. And then do we get a final answer of 4.038? And sure enough, that's exactly what we got. So there's our final 3 marks there. And we've got the correct units as we went. Minimizing, insulate the calorimeter, use a lid, transfer the copper pieces quickly, use cold water, avoid splashing. We have avoid splashing, use cold water, use a lid, insulate calorimeter. So that is also worth any 2, 6 and 6. What? 12 marks for that. Yikes. Well, great stuff. Okay, so there's another 12. And then finally, smaller percentage error. Okay, -1 of percent emitted. Well, I had the word, so that'd be fine. A greater rise in temperature. Why would adding large mass improve the accuracy? A greater rise or change in water temperature, which would lead to smaller percentage error, is what you're basically getting at there, and that's our final 3 marks. Okay, that is the only question so far. The only time he's asked this experiment, it was 2007, but again, it can creep into the long questions, so to get yourself familiar with it, it's a good one to try and practice. Best of luck with your Leaving Cert. Hope you found that useful. If you did, then like or subscribe, or check out the other social medias where I'll be adding extra resources. If you want something particular made, then just leave me a message on one of those platforms and I'll do my best to get around to it at some point. Best of luck in all your exams.